Hey Wiley.
What is? Oh,
Yo. How are
yeah,
you? Doing-
good.
That's good?
I'm. It's just a really busy week.
Yeah, I know. It's been so busy. I have two midterms tomorrow, one midterm on Friday, and the quiz on Friday. So, I've been
Hmm.
studying for that.
Yeah, I got a quiz Friday and then a midterm Friday. So
Oh, which
yeah,
classes?
Latin quiz and then this to be exam.
Oh, I
I'm
see.
just yeah.
Uh-huh. Uh-huh.
Uh,
Is this the first Biz to be exam?
yeah,
Oh, okay, okay.
and let's see.
Yeah.
All the Helix students took their exams. So
Yeah, they did.
no,
I know. No, no, no. Yeah, I didn't prepare anything. I was just
it's okay.
basically
It's okay.
yeah studying for my exams tomorrow and Friday.
Yeah.
Mm.
Could you explain for ring opening?
Ring opening, yeah,
Yeah.
there's different ring openings. So what ring opening did you want to go
No,
over?
just like the concept itself of
Uh-huh.
if it's acid catalyzed,
Oh yes.
why does it go to the more
Mm,
subside?
yeah, for epoxide.
Yeah.
Yeah. Okay. So epoxides, we can have more subside and then less subside. So let's say we have this epoxide right here.
Yeah.
There's two conditions we can react this with, acidic conditions versus basic conditions. In basic conditions, let's say we use NaOCH2CH3 and the solvent is the
Left
neutral version of
oxide.
that. Whenever
Mhm.
you see Na, that's the positive charge, and whatever is attached to it is a negative charge. So we know we're in basic conditions because we have a negatively charged molecule here. And actually, I'm going to do this in two steps. The first step is going to have that negative charge with its neutral version, the solvent.
Mhm.
And the second step is going to be some acid workup. Now, this ethoxide right here with the negative charge is a strong enough nucleophile to attack this epoxide directly and kick
Mhm.
off the leaving group. And think of this as a strictly SN2 reaction, right?
Mhm.
They will have all SN2 properties. So SN2 reactions prefer to attack the less subside because there's
Yeah.
less steric hindrance there,
Seconds.
right?
Yeah.
And it also will invert stereochemistry. So this O minus here is going to attack this less subside, and when we break open the ring, that inverts this wedge bond that we're breaking onto a dash. Because when this O minus approaches this carbon here, it's approaching it on the back side, the opposite side of whatever bond it's breaking right there. So when we make the new bond between this carbon and this oxygen, that new bond is going to be a dash, which is the opposite of that wedge right there that we're breaking off,
Okay,
right?
I see.
So this methyl here stays as a dash. This oxygen here of the epoxide is now negatively charged because it gains a pair of electrons from that bond being broken right here. And this wedge bond right here stays as a wedge because nothing touches that carbon. But the new bond here between that carbon and oxygen, this new bond here is a dash because this came from a backside attack, like that.
Yeah.
Right. Now, this oxygen here, we see that it's attached to a CH2, CH3, like that. So this right here is our final product after the first reaction, right?
Mhm.
Where now to make the product stable and neutral, we bring in the acid workup H3O plus to protonate the O minus to make it neutral OH, neutral, right?
I see. I see.
So that's opening up an epoxide in basic conditions where everything is strictly SN2. The regional selectivity is SN2, meaning that we attack the less subside, and the stereo selectivity is SN2. We did a backside attack to invert the stereochemistry, right? So everything was SN2 in this reaction in basic conditions. Now, if I react the same epoxide with the same more and less subside in acidic conditions this time, it's gonna be a different sort of reaction, right? So let's say we use ethanol and H2SO4 strong acid.
Mhm.
We are in acidic conditions because we have a strong acid present, sulfuric acid. This neutral ethanol here is a weak nucleophile because it is neutral. There's no negative charge there. And because it's weak, it cannot directly attack the epoxide right away. In the previous example, this strong nucleophile with the O minus negative charge is strong enough to attack the epoxide right away, right?
Mhm.
But this weak nucleophile here can't do that. What we have to do is we have to react this epoxide with the strong acid. So the first step is going to be an acid-base reaction. We're going to protonate the epoxide using H2SO4 here. Kick out the HSO4 minus to get this protonated oxygen with a positive charge. Now, you can think of this as a good leaving group, the OH plus. Right? That is going to like either leave in two ways. It could leave this way, or it could leave this way, like that, right there, right? If it leaves this way, we're gonna form this carbocation. If it leaves that way, we're going to have this carbocation right here. Which carbocation would you say is more stable?
First.
Yeah, first one, right? Because the more substituted the carbocation is, the more stable it's going to be. So the more substituted carbon here will have a bigger partial positive charge, and the less substituted carbon here will have a smaller positive charge.
Okay.
So when we do this reaction, it will have a mix of both SN1 and SN2 properties. The SN1 property is the regional selectivity of it, meaning where it attacks. Right? So it prefers to attack the more subcarbon because there is a more stable positive charge there. There's a bigger positive charge on that position, the more sub position. The SN2 property of it is the stereo selectivity part, which is the backside attack.
Oh, okay.
Invert stereochemistry, backside attack. Great. So now the ethanol, the neutral alcohol that we have, is going to attack this activated electrophile. And it's going to attack the more sub side because there's a bigger positive charge there, inverting this stereochemistry that we're breaking off. So when we draw out the product, this wedged OH right here stays as a wedge because nothing touches that carbon. And this OH right here is this epoxide OH right there. The oxygen was positively charged, but it's now neutral because it gained a pair of electrons from this bond here being broken off. This is the new bond being formed between the carbon and oxygen. This dash methyl right here is going to become a wedged methyl like that. Now, this oxygen here that attacked that carbon is attached to an ethyl group, a hydrogen, and one pair of electrons, giving it a positive charge. So the last thing was just to neutralize it by deprotonating it with HSO4 minus and making it neutral. Right. Okay. So opening up epoxides or opening up a ring in acidic conditions is trickier than basic conditions, right? Because it's going to have both SN1 and SN2 properties where you attack the more subside and invert stereochemistry. Whereas in basic conditions, it's more simple because it's strictly SN2, right? The regional selectivity is SN2, you attack the less subside, and the stereo selectivity is SN2. You invert the stereochemistry. So it's like an actual SN2 reaction, right? Single step backside attack at the less subcarbon in the basic conditions, right? Okay. So you can say the same for bromonium ion rings or mercuric ion rings for oxymercuration demercuration, right? It doesn't have to be an epoxide. Whenever you see like Br2 with water or alcohol, you're gonna get this bromonium ion ring right here, which is why when you see this positively charged three-membered ring, think of acidic conditions, because we could either kick off the leaving group this way or this way, and we know that the positive charge is bigger at the more sub position because it's more stable there, which is why any nucleophile like alcohol or water would prefer to attack the more sub side when we have a positively charged three-membered ring like that.
Okay. Yeah,
it doesn't have to be that bromonium ion ring. It could also be this mercuric ion for oxymercuration demercuration, which is why it's a Markov-Nakov reaction. Yeah. Okay. Like that. Yes. Okay. Are you learning about epoxides right now in 128B?
Yeah, we just finished epoxides. We finished epoxides. Then we talked about crown ethers, and then now today we talked about and finished IR spec, and now we're doing on NMR.
Oh, NMR. Oh, you're learning NMR right now for
Just
128B?
today we just talked about the concept of like, oh,
Oh,
you put a big magnet in this like big
uh-huh.
magnet thing, you
Yeah.
blast radio waves,
Oh my gosh. Like
and then
HNMR, right? Hydrogen
yeah,
or
yeah, yeah,
okay, okay.
and
Did you
then
guys learn about IR or did you
yeah, no,
guys
we just covered IR.
Oh, okay, okay. And then you only learned that last quarter, huh? Like with all the
No,
controlling
I didn't
matrix.
learn IR or any spec last quarter, so it's
Oh
all
yeah,
good.
yeah, yeah, yeah. You didn't learn it in 128A, but you learned it
Yeah, yeah,
when you
yeah.
did the Kahoot during one of our
Kind of,
sessions.
yeah.
Yeah, yeah. In one session too. That's
He
that's
finished everything in IR.
oh my
That's the
God.
deal.
Yeah,
Yeah,
that's good. Okay. Uh,
that's all I got.
okay, I see. Okay. When's your next test or exam for 128B?
Next Friday,
Next Friday. Okay, okay. That's
and it's
good.
gonna be NMR on
Mm.
it.
Oh my God. With all the like analyzing integration, coupling, constant
I think
n
so.
plus one
Yeah, he gives
rho
us like
meters.
the J values or whatever.
Oh my gosh.
Yeah,
Yeah, that like when I took OChem was the hardest section on the exam, like the NMR, for me. Like harder than synthesis, harder than predicted product, harder than mechanism, conceptual
yeah,
pressure, nomenclature. Because it was hard to pick up, yeah, like yeah, hard to like get the correct specific structure, you know?
yeah, yeah.
Yeah. Okay. Hey Jenna, hey Madison.
Hi.
Hello. I didn't prepare anything for today's session, so it's gonna be more of like a drop-in kind of session where if you guys have questions, we could go over that, or if you guys have the practice quiz, we could go over that as well.
Okay.
Uh-huh.
Um, I was wondering if we could go over different kinds of nomenclature because the quiz is gonna be on um aromatic nomenclature and
Mm.
ethers.
Yes. So nomenclature, I gotta look at the rules for that. 'Cause I'm a little bit rusty on that. So let me see here for nomenclature. Uh, Oh, and Madison, did you update the folder with the recent lecture slides on the Google Drive?
I did not. I completely forgot about
Oh,
that.
it's okay, it's okay. Yeah. So let me find nomenclature. Mhm. Okay. Uh, uh, um. See. Mm. Yeah. So for ethers, this is what we have. Um, Let me find the aromaticity. 1, 2, 2. Aromatic 1. Okay. So ethers are the functional group ROR, where R is any random hydrocarbon chain and O is the oxygen. So if we look at this ether here, this is the R on the left side, this is the R on the right side. 1-ethoxypropane. So the main chain is going to be the longest chain. Our longest chain is going to be numbered like this: 1, 2, 3. That's our longest chain. And our substituent is going to be that OR group right there. So OR is considered our substituent in the name. And we see that at carbon 1 of the main chain, our main chain is going to be this propane right there. At carbon 1, there is an OR group where the R group is 2 carbons long, right? And because it's 2 carbons long, it's going to start with eth, right? Meth for 1, eth for 2, prop for 3, bute for 4, pent for 5, hex for 6. And oxy, when you see oxy, then that's going to show that you have an OR substituent, right? And then propane here is our main chain. 1, 2, 3, main chain. Okay. And when you have alcohol in the molecule, alcohol will have a higher priority than ethers. So we have alcohol here. Our number system will go like this now, left to right. 1, 2, 3, 4, 5, 6, 7. We see that at carbon 4, there is a OR group attached to carbon 4. And the R group is 1 carbon long. So it's going to start with meth, right? Because it's 1 carbon long. And we have oxy because it's OR, right? So 4-methoxy, 2-heptanol, because at carbon 2, there's an alcohol right there. You could have also written this as the name as well: 4-methoxy hept 10-2-O, right? And this is the way that I recommend doing it, because if you have alkenes or any other functional group, you could clearly see where the alcohol is at more clearly in this name, right? Which is on carbon 2. But in this case, this is also acceptable right here, right? Now for cyclic ethers right here, we see that this is also an ROR, but it's in a ring cycle. So if this is the only functional group here, our atom 1 is going to be the oxygen atom. And our main chain is going to be oxa, cyclo, however long the ring is. In this case, it's a 6-membered ring, right? Because we have 1, 2, 3, 4, 5, 6 hexane, right? It was a 5-membered ring like this. Then that would be oxa, cyclo, pentane, right? Because this ring here is 5 atoms big: 1, 2, 3, 4, 5. But this ring here is 6 atoms big: 1, 2, 3, 4, 5, 6. And I want the lowest number to be on the next substituent, so I'm going to number it going this way, which is counterclockwise: 1, 2, 3, 4, 5, 6. And at carbon 2, I have a methyl group there, so we have 2-methyl oxacyclohexane. Okay. There's some common names as well that you might have to memorize, like this diethyl ether, where you have 2 ethyl groups attached to this oxygen, is all just known as regular ether, right? And this is a common solvent for many reactions, because this ether here is aprotic, there's no hydrogen bonds, and it is very stable, right? Very stable. there's not a lot of partial charges, so it's gonna be inert, unreactive, which is a good aperiodic solvent for many reactions. Right? It will not interfere with the mechanism. Unreactive, inert. For this ether here, we have two R groups. We have a methyl group and a tert-butyl group. So the name here is methyl tert-butyl ether, and that can be abbreviated as MTBE. This is butyl ethyl ether, where we have 1, 2, 3, 4 carbons, 1, 2 carbons there. And butyl comes first because B comes before E. Right, so this is alphabetical order here. In the last example here, I thought T did not count in the alphabetical order, so I thought tert-butyl would go first before M, but they put M before tert-butyl. So I'm guessing T counts. What is it? Yeah, because M goes before T. So if that's the case, then T does count in the alphabetical order, right? Because if T did not count, then this tert-butyl would have been in the first word, right?
I have a question on that one.
Yeah.
Why wouldn't it be like methoxy?
Methoxy.
Yeah, on that one. Like methoxy tert-butyl.
Right. So if the longest chain was this right here, where it's 3 carbons long, 1, 2, 3, we could say that we have 2 methoxy, and we also have 2 methyl. So let's say that's 2 methoxy, 2 methyl propane, right? Because our longest chain could be this 3 carbon long chain right there, where there's 2 substituents, a methyl group on carbon 2 and a methoxy group on carbon 2. So that could have given you 2 methoxy, 2 methyl propane. But let me double check if that is actually a thing, another name for that. 2 methoxy, 2 methyl propane. Two methoxy, 2 methyl propane. Yeah. So that is another name for it, right? This methyl tert-butyl ether here is also known as 2 methoxy, 2 methyl propane. You could have
Okay.
done that as well.
Okay, I just watched a video on this, so I was like,
Yeah.
good review again.
That's good. Yeah.
It makes sense because like you're kind of like you're able to like break off like the sides, right? Like where the oxygen is attached, like that methyl group, like you kind of break that off, and that's one, and then you have like the butyl group on the side.
The tert-butyl group on the side, yes.
Yeah.
And if we're sticking with that, right, then we don't say this is tert-butyl. If we want to do like the full IUPAC name without using any common names, we can't use tert-butyl. We actually have to find out what's the longest chain here, which is this 3 carbon chain right here, 1, 2, 3. It could have been 1, 2, 3 as well. It doesn't matter. So the longest chain here is propane 2, and then the carbon 2. There's a methyl group right there. If we want to use tert-butyl, then we have to use the common IUPAC name substituent for the other R group as well. Right.
Okay.
Yeah, there's multiple correct names for this here.
And also, just to clarify, if that methyl group on the far left-hand side was an ethyl, A, B, C, D, E. So would it have priority over the methoxy? So it would be, what is that? 2 ethyl, 2 methoxy?
Oh, if it was something like this. Oh wait, shoot, like this right here. Like an ethyl group here and a methyl group right there.
Yeah.
Yeah. So the longest chain would be this 2 carbon chain. Highlight that like that. So that would be we could say 1, methoxy ethane, because our longest chain is 2 carbons long, that's ethane, where at carbon 1 there's a methoxy group. Or we could say ethyl, methyl, ether. Let me double check this if
Okay.
they're the same thing. 1 methoxy ethane. Yes, that is 1 methoxy ethane. Now let me search up ethyl methyl ether. Ethyl methyl ether. Yeah, that's also the same. Methoxy ethane. Methoxy ethane. Yep. This one here is optional because when we say just methoxy ethane, the methoxy group, this OR group, can only go on one of 2 carbons, this carbon or that carbon. And then it doesn't matter which carbon we put at, right? If we put in this carbon, it's 1 methoxyethane. If we put it on this carbon, it's also 1 methoxyethane. So it doesn't really matter here. But if we had a longer parent chain, like butane, pentane, hexane, then we would have to put the number because it does matter where we put the OR group, right? 1, 2, or 3. Or actually,
Okay.
yeah. But in this case, 1 is optional.
Okay.
So is the rule to always put the R group before the longer chain and then add an oxy to that R group?
Yeah, so when you see oxy, that's a substituent, right? If I circled this whole 1 methoxy right there, that's that whole substituent there on carbon 1, right? This is the methoxy group on carbon 1. You could do it like that, or if it's a simple ether like this, you could shorthand it by saying like ether at the end and saying the 2 substituents attached to that oxygen as a substituent, right? So we have 2 carbons here, so we could say that that's ethyl. 1 carbon here, we could say that that's methyl. But that's like more of the common name of ethers. If you want to do like the full IUPAC name, then you want to use oxy, I would say, as a substituent, and then the main chain as whatever the main chain is, right? So oxy would be the OR group, where the R group is the shorter R group compared to the other R group, right? So if I give you another ether like this, right, how would you name this ether here?
Wait, let me write this down.
Yeah.
So our longer chain has 1, 2, 3, 4, 5. So we have a pentane. And then our substituent is an ethyl. So that would turn into an ethoxy.
Right, because if I highlight the main chain here, 1, 2, 3, 4, 5, at carbon 1, we have an ethoxy right there. Like, I'm gonna circle all of our substituents in blue. Those are all of our substituents right there, where that substituent right here is ethoxy, right? So we have 1 ethoxy. And what are our other substituents, and how would we present them in our name, in our IUPAC name?
Wait, before that, you put 1 as the ethoxy. Is it always just gonna be 1 in that case if we're naming this substituent, because like it just always ends up after the oxygen, so it would be 1, or no?
Doesn't have to always be 1, because if I give you this ether here, it would be different, right? But let's focus on this one first, where the ether is going to be on carbon 1, but this one here, the oxy would not be on carbon 1, right?
Okay. So this is 1 ethoxy, 1 methyl, 1, 2 dimethyl.
1, 2 dimethyl.
And then 3 ethyl.
3 ethyl. And
Or
we have
no.
pentane as the base name,
Yeah.
right? So now we have
So
our list of substituents. Then what do we do?
ethyl would be first because we're doing, or no, would it be ethoxy? Is
ETH,
ethoxy?
ETH, yeah, ethoxy, because ETH cancels out and then O comes before Y, so it would be ethoxy first, right?
Oh, I thought oxy is always gonna be first, or is that not true?
It's not always gonna be first. It's gonna be based on the alphabetical order, right?
Okay.
If this was a butyl somehow, like with the B, then that would go first because that has
Okay.
the first letter, right?
Okay.
Mhm.
So we would do 1 ethoxy,
Mhm.
3 ethyl, 1 2-dimethylpentane.
1,2-dimethylpentane. Yes, and the D in di here does not count in the alphabetical order. We ignore that and we go to M, which comes after E. So that is correct, right?
Okay.
Yep. So that is the name for this ether here. Okay, let's try this one here.
Oh, that one.
Mhm. Yeah.
So our longest chain is 1 2 3 4 5 6 7. So that's a heptane.
Heptane. And how did you number it? Left to right like this or right to left?
Well, both of them have a substituent on like number 1
And then
or number
what about the
2.
second substituent? Where would the second substituent go? Like what's the way where the second substituent is on the lower number?
Oh, yeah. So if you're going from right to left, we don't have a substituent, so we would go left to right.
Yes, that's how you would do it if it was 7 chromosomes long, but the main chain is actually longer than that. Try to find the longer
Oh,
chain.
is it from the tert-butyl?
Yes.
Okay.
Going like this right here. Yeah.
Okay,
So
that's
that would be 1, 2, 3, 4, 5, 6, 7, 8. So be careful of that. The main chain is not always gonna be clean, like in a zigzag horizontal line like that. She can be
yeah.
tricky and put the main chain up like that or down like that.
Okay.
Right. So in our highlight here, this is our main chain right here.
So we have an octane. And then wait. Would we still name that substituent tert-butyl at number 3?
At carbon 3, there is no tert-butyl. There is a methyl at carbon 3.
Oh.
Right. And we have, if I circle the substituents in blue here, that's a substituent, this is a substituent, that's a substituent, this is a substituent, that's a substituent, and this is a substituent.
Oh, we have to look at it relative to the chain because I was looking at it from like how I saw it before.
How you saw it before, right? That's, if you saw it like that, then this would be tert-butyl. But we cannot count this part as the substituent because that's the main chain right there. Yes.
Okay, that makes sense.
Yeah.
So we have a methyl at 3.
Yep.
3 methyl.
How many methyls do we have overall in the entire molecule?
Oh.
And how many carbons?
1, 2, 3, 4.
4. So we gotta put 4 numbers and tetramethyl. Right, 4 numbers dash tetramethyl.
Okay.
So it would be 2, 2, 3, 7 dash tetramethyl.
Yeah. And then at number 4 we have is it a methoxy?
It is a methoxy, right?
Okay.
Yep.
So that's 4 methoxy. And then 5 would be ethyl.
Yep. 5 ethyl, like that.
Okay, so and then we have an octane.
Yes, and then we have an octane, right?
So we would start with ethyl because we're doing it in alphabetical order. So 5 ethyl A, B,
5
okay,
ethyl.
and next 4 methoxy.
Yep.
And then tetramethyl.
4 methoxy. Yep. And then 2, 2, 3, 7 dash tetramethyl octane. Yep, that's right. Right. So be careful of what the longest chain is, and from that longest chain, use that as a reference point for all the other substituents. And if you have multiple of the same substituents, group them together in numbers, and however many there are, do like di, tri, or tetra.
Okay.
And that di, tri, or method does not count in the alphabetical order.
Okay.
Right? Yeah. Let me give you one more ether nomenclature here. It's gonna be this right here. Let me make it a little bit tougher for you guys.
Oh.
Yeah.
Oh,
Yes.
stereochemistry.
Yes, stereochemistry. RNS.
Oh my god.
Does Levin's 8B class have different sections, or is everyone in the same section, same lecture, same exam times?
I think there's only one class.
Okay,
8 a.m.
okay. 8 a.m.
Yeah.
So everyone takes the quiz at the same time.
Yeah.
Everything. Okay,
Yeah.
okay. Yeah. I got 2 midterms tomorrow. Midterm on Friday and a quiz.
Oh my god,
my
it's
stress.
supposed to be
You
office
do?
hours.
Yes.
Wait, you have 2 midterms tomorrow?
Yes, I do, but I
Oh
gotta
my
do these
gosh.
office hours. I gotta do it.
No.
It's mandatory. It's mandatory.
That's insane. Do you feel ready or no?
Not really, but
my god.
I'll focus after this office hours.
Oh my gosh.
I got all the resources prepared. I got all the practice problems prepared, so I have a clear plan of what to do. Like, I'm not lost on what I need to do. So right after this, I'm gonna like do that plan. And then,
Okay,
like,
that's
get
good.
into it. Yes.
Holy moly.
Okay, we'll make sure to finish at 10.
Thank you.
Of
Oh my
course, of
gosh.
course.
If you have time
Yeah.
to go over like those reaction problems on the quiz.
The practice quiz? Yeah.
Yeah.
Let's do that.
I think I understand like most of the vocab and stuff. I'm just gonna like rewatch some like videos that kind of break it down because I think
Mhm.
that helps more like on each individual thing.
Mhm.
But the reactions is like probably the thing I struggle with like the most.
Like recognizing the reagent and associating it with what reaction and the mechanism as well, like arrow pushing the charge, the pairs of electrons, the side products.
Yeah, like the
Yeah,
whole thing. Like
the
I
whole thing.
understand I can like get by with the vocab and everything and like
Yeah.
kind of the rest, like the aromatic, non-aromatic, like all of that conceptual stuff, but how things move is like my downfall.
Oh yeah. Oh my gosh, like the arrows. Oh my god.
Yeah.
Yeah. That's very specific. Okay, let's go over that on the quiz. Uh-huh.
Okay.
Uh-huh.
I before we do that, I just finished the oh, I forgot the stereochemistry. Never mind.
Stereochemistry. Well,
But
what do we have so far? Yeah.
I
Uh-huh.
put 1 bromo, 2 chloro, 4
Wait,
iso. Is that wrong?
So how did you number the ring here? What's the number one atom?
I put the bromine, but I think that's wrong. Was I supposed to start at the oxygen?
Yes, when you have a cyclic ether, our number one atom is always the oxygen in the ring, like that, right?
Okay.
Uh-huh. And
So,
this is our number one atom right here. Now, do we want to go clockwise or do we want to go counterclockwise?
clockwise, right? I mean, wait. Yeah, clockwise, right?
Clockwise, yes, it is. It is. Right,
Okay.
right, right. You are correct because we do hit the same amount of substituents either way. If we go clockwise, we have our first substituent on carbon 1, second substituent on carbon 5, and third substituent on carbon 7. That's the same exact thing as if we went counterclockwise. First substituent on 1, second on 5, third on 7 if we went counterclockwise. So because there's a tie, and all of these substituents are equal priority, then we look at alphabetical order. Br, bromine, bromo comes first before chloro. So that's why we go clockwise. Right.
Okay.
Yep.
So it would be 2 bromo.
Uh-huh.
Wait. Oh, okay. That makes sense. Okay, 2 bromo and then 5. I know that's an isopropyl, but isopropoxy sounds wrong.
Not isopropoxy, because isopropoxy would be this substituent instead. Right? That's isopropoxy. Because isopropoxy. When you see oxy, that's OR. Right? There's no OR here. Right? So that is just isopropyl. Isopropyl with a YL.
We would see an OR at the isopropyl.
Like the OR is the isopropyl. So this is the O right here, and the R is the isopropyl right there. And if you have that in the substituent, then that's isopropoxy.
Oh,
right. So if we have something like this, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, and at carbon 2, we have that right there, then this is 2 isopropoxy octane.
Okay.
Right. But this is not isopropoxy because there's no O oxygen there. Right.
Oh,
it's just an isopropyl group right there.
Okay, that makes sense.
Yeah.
So it would just be 5 propoxy. No, wait, there's no O.
No O, so we cannot put oxy.
So
right.
just isopropyl.
Yes, just 5 isopropyl.
Okay.
Right. Yep.
Got it.
But what comes first? And the I in isopropyl counts. Does I or C come first?
C.
C, right. So before that, we are going to put 7 chloro.
Oh, okay, 7.
right? The number here does not matter, right? Because it's gonna be 2, 7, and then 5. What matters here is the alphabet. B comes first, and then C, and then I. So
Yeah.
the next one would be 5, isopropyl.
Okay.
Right. Mhm.
Isopropyl. And then we can't just say cyclohexane, right? It's
Yeah, we cannot.
oxacyclo.
Yeah, it's oxa, cyclo, not hexane, but heptane, because our ring is 7-member ring.
Oh, 7. I missed the 7.
Mhm.
Oxycycloheptane.
Yes.
Okay.
Now, the stereochemistry. Are you guys comfortable with doing it quickly, or do you guys have to like do it like one by one?
Okay with it, but
Okay with it, yeah.
if we need to cover other things, it's fine.
Right. Let me just do each one for you guys here, so for you guys to check afterwards, for you guys to try. That's blue, that's pink, this is green. The blue one, that's 1, that's 2, that's 3. Going this way is S, and it stays S because the hydrogen is on the lowest priority already. For pink, that is 1, that is 2, that is 3. Going this way, it looks R, but it's actually S because the lowest priority group is on the wedge. So we flip what it actually looks like right there. For green, so there's a tie here and a tie here, but bromine beats chlorine, right? In atomic number, I think bromine is below chlorine. Let's see, Gen Chem. See, bromine. Wait, periodic table. Periodic table. I think bromine beats chlorine. Yes. Bromine beats chlorine. So this is 1, that's 2, this is 3. Going this way is S, and it stays S because our lowest priority group is on the dash already, right? So it would be 2.
Oh yeah. Okay.
S, 5, S, 7, S. Oh, so it's all S's here. I did not intend to make it all S's, but it has to be all S. SSS. That's good. Triple S.
Well, one of them was R, but it's actually S.
One of them looks R, but we flipped it to S, right? Because I made it a dash, and then that made it flip to S. Yeah.
Yeah.
Right. That's good. Okay. So that is probably like overkill on nomenclature again because it's like so long. Yeah. Right. Okay. Let's do the practice quiz, mechanism, and predict the product reactions. Yeah.
Yes.
Let's go to the drive.
If we could focus on like B, I
B?
think that's the hardest one.
Okay.
I think the other ones, like you can, this sounds really bad, but like you can like memorize like how they react.
Yeah. Like for predict the product. Oh, reactions, like the first section. Reactions. Yeah. Yes. B. Oh yeah, B is the one that you have to actually think about, and the other ones are like more predictable, you could say, like predictable on how they react.
Right, because like it like kind of like breaks off, and then one gets added onto the other side of the OH group.
Right. Yes. Share screen. Start. Okay. So I went over this with Wiley at the beginning of the session. This B right here is an epoxide, a 3-membered ether, which is an epoxide. And our reagents here are this RONA and ROH. Whenever you see Na, associate that with a positive charge, right? The same goes for potassium K. When you see Na or K, that is going to be positively charged.
Right.
That means that whatever is attached to it is negatively charged. So our negatively charged species here is at RO minus, right? And because we have that negative charge, we are in basic conditions. that negatively charged oxygen is our base here. Basic conditions. And in basic conditions, it's going to be strictly SN2 reaction. The regiochemistry SN2 and the stereochemistry SN2. So in SN2 reactions, we prefer to attack the side that has the least steric hindrance, the side that has the most space available for this OR minus to attack.
Right.
We have two partial positive carbons here. We have this partial positive carbon and this partial positive carbon. One is more sub, one is less sub. Which one would you say the OR minus would attack, A or B? If this is strictly SN2, everything B, right? So when we attack that less sub side, we're also gonna invert the stereochemistry and kick off that bond like that because we're doing a backside attack. This RO minus here, when it attacks that carbon, it's approaching on the backside of this wedge right here, which is a dash.
So then it becomes a dash.
Yes, that new
Where
bond
B was okay.
becomes a dash, which is that dash right there, between this carbon and oxygen right there. And this is the step where a lot of students forget. This oxygen here is attached to this whole R group. That R group follows that oxygen because it's still attached to that R group right there.
Okay, I see.
Right. So that oxygen there is attached to 1, 2, 3 carbons, a propyl group. 1, 2, 3 carbons, a propyl group. And you could draw.
So it just adds on to the oxygen.
It follows along, like it's always there. It doesn't get ripped off.
Okay.
It always follows along, and you could draw it like this. You could draw it right here. You could draw it right there. However way you want to draw it, as long as it's there.
Okay.
Right. Now this O minus here is now neutral because it gained a bond and it has 2 bonds now. Neutral. Right. This ethyl here that was on the other side stays as a dash because nothing touches that carbon. Right. Nothing touches this carbon right here. This wedge oxygen there, like stays as a wedged oxygen right here. So we didn't really kick out the oxygen of the molecule here because that oxygen that got kicked off is this oxygen right here, right? We just broke open the ring. This was a 3-membered ring right here. We broke this bond, but the oxygen is still attached to the molecule overall, to this carbon right here. And that wedge bond stays untouched, so it stays as a wedge. And this oxygen here, because it gained a pair of electrons from that bond, it is now negatively charged like that.
Okay.
Right? And then from here, we could use this product solvent as a acid for this O minus to grab the hydrogen, the bond between this hydrogen and oxygen, right? Because this O minus is trying to grab that hydrogen away from this oxygen, that bond is going to break and go onto that oxygen right there to give us this final product there.
The product solvent came from the bottom from OH.
Yeah,
right?
This bottom over here, ROH. Yeah, that was given.
And then the first part, that first oxygen attached to the 3 carbons, came from the top O and A.
Yes.
Okay.
This O CH2 CH2 CH3 came from this O CH2 CH2 CH3 right here that attacked that carbon right there. Right.
Okay.
If I highlight it in yellow like this, that's this yellow OR, yellow OR, yellow OR right there, like that.
Okay, that makes sense.
Yeah. And if I highlight the epoxide oxygen in pink, like this, that's this pink oxygen right there, all throughout. Like this one, and that one. That's the same oxygen.
Oh, okay, I see.
Right. Yep. Yeah.
Oh, gosh. We just went over this. I remember going over this in, like, our session. But like, I mean, like seeing it again, it makes more
excites
sense.
to click more, right?
Yeah.
This right here is basic conditions where we attack the less side and invert stereochemistry, which is I would say the easier conditions. The harder conditions, I would say, like mechanism wise, is the acidic conditions, right? So let's use the same epoxide, but I give you different reagents here. Instead of basic conditions, we're going to use acidic conditions, where the reagents here are going to be, let's say, isopropanol, right? Not isopropyl, but isopropanol with an alcohol, and H2SO4 acid. Now, the mechanism is going to be longer for sure, because this isopropanol here cannot attack any part of the epoxide at all, because this is a weak neutral nucleophile.
Right.
Right. So this strong acid here, sulfuric acid, is going to protonate the epoxide oxygen. Okay. Yes, that's the very first step, an acid-base reaction. We protonate the epoxide oxygen with the strong acid we have. That's the very first step. Okay, when we do that, this oxygen here gains a bond to hydrogen like that. That's the new bond that gained right there. And because it has 3 bonds now, it is positively charged, right? So that's the other tricky part about this mechanism, like keeping track of the formal charges of each atom. When it gains a bond, when it loses a
Right.
bond, like you have to be very familiar with what formal charge an atom will have, depending on how many bonds they have, right? And the common ones that you have to be familiar with are oxygen, nitrogen, and carbon, and halogen,
Okay.
right? So let me write that down. The carbon, oxygen, nitrogen, halogen. Like these are the like atoms you have to know the formal charges for sure. Like when they're negatively charged, when they're neutral, and when they're positively charged.
Right.
Oxygen with 3 bonds is positively charged. Oxygen with 2 bonds is neutral. Oxygen with 1 bond is negatively charged. Wait, did I say positively charged or negative charged with 3 bonds per oxygen here?
Positive?
But yeah,
I think
positive
it's a
charge.
positive, yeah.
Right. Uh-huh. Yep, oxygen with 3 bonds is positive charge. Oxygen with 1 bond is negative charge. Oxygen with 2 bonds is oxygen. It is neutral. Okay? So now, once we have this positively charged oxygen right here, think of this as a good leaving group. Right? So now, we can kick off the ring by itself that way, forming the more substituted carbocation, or
Mhm.
the other way, forming the less substituted carbocation. Right? And the carbocation is going to be more stable on the more substituted side because of more hyperconjugation. You could think of it as friends.
Right.
So there's a bigger positive charge living at that more subside, and a smaller positive charge living at that less subside. Right? So
Okay.
that's why now the alcohol, whatever it is, it could be methanol, ethanol, propanol. In this case, I give you isopropanol.
Mm-hmm.
Is attracted to the more subside because there's a bigger positive charge there, right? The electrophile is stronger at the more subside because there's a bigger positive charge there.
Right.
So when we attack that, we still do backside attack and invert this stereochemistry right there. It's going on the backside of this wedge, so the new bond will become a dash, right? So let's draw on that template right there. I'm gonna draw out the other carbon first because that's the easier one. This wedge bond right here that stays untouched is
Right.
gonna maintain as a wedge, which is attached to this OH right here.
Mm-hmm.
OH. And now this oxygen here we see has 2 bonds, one to that carbon, another one to that hydrogen right there. Right?
Okay.
And that's natural because it gained a pair of electrons.
Right.
Right. Now this is the hard part where we invert the stereochemistry. I'm gonna draw out the new bond, which is the dash, because we did a backside attack.
Mm-hmm.
That's gonna be between that carbon and oxygen right here. Right? And that forces this dash ethyl to become a wedge ethyl because we invert the stereochemistry at that carbon that we attacked.
Yeah, that makes sense.
Now, what is attached to this oxygen here? Like what came with the oxygen? What followed the oxygen when it attacked this carbon?
The hydrogen. Wait,
The hydrogen, yes, and that R group as well.
Okay.
Isopropyl. Right, so the hydrogen and isopropyl follows that group. If I highlight it in yellow like this, boom, highlight in yellow, that's this yellow part right there.
Right. Okay.
Yep, and this right here is the new bond that was inverted. Now, oxygen with 3 bonds would have what form of charge?
Oxygen with 3 bonds. That's what, 1,
And 1 pair of electrons.
3, 4. Oxygen wants 6.
Mm-hmm.
So it's positive 2.
Mm-hmm.
Or is
what-
it just positive? Wait, 1, 2, 3, 4, 5.
Mm-hmm.
Okay. So then it's just a positive.
Just a 1 positive charge, right? Because that's 3 bonds and 1 pair of electrons. And
Each bond. Sorry, each bond counts for one electron, correct?
Yes, when we calculate formal charge. Yes.
Okay.
When we
just
calculate
wanna
formal charge.
make sure.
Yeah. But not when we calculate like how many bonds they have in total. Right.
Okay.
It's only for like when we calculate formal charge.
Okay.
Yeah. Right. Because I don't want you to think about like each bond counts as 1 electron because each bond has 2 electrons.
Right.
But 1 electron belongs to that oxygen right there for each bond.
Okay. I see. That makes sense.
Right. Okay. So now the last step here is we want to get rid of that positive charge because that's unstable. We don't want that charge at all. Right. And what we're gonna use is this thing that we kicked out at the beginning.
So 4. Okay.
HSO4 minus, right, grabs that hydrogen. The bond between that hydrogen being grabbed and oxygen right there, those 2 electrons in that bond are gonna break and go to the oxygen like that,
Okay.
which makes that oxygen neutral now.
Because it has 6 electrons.
Yes.
Okay.
1, 2, 3, 4, 5, 6 electrons to itself, right? Like
Right.
that belongs to itself. But overall, if you count the shared electrons, it has 8 electrons, which fulfills the octet rule, right? So don't say that oxygen has 6 electrons because that's gonna be so wrong. Doesn't fulfill the octet rule. That's not
Okay.
good. That's only what we think about when we calculate thermal charge.
Okay. That's totally fine.
Yep. Right. But because like this is 2, 4, 6, 8 electrons. That's 8
Mhm.
electrons. But if you calculate formal charge, you calculate how many electrons it has to itself.
Right.
Yeah. Right.
Okay, and then that you don't include that HSO4 like at all in your answer, correct? Even though it's just like I say floating around, but
Yeah.
That's-
In the predicted product reactions, you don't have to put that. But in the
Okay.
mechanism problem where you have to draw out each arrow, each charge, and each side product, you do have to put that
You
in.
put that in. Okay.
Yeah. Right.
Okay, that's good to know.
Yeah.
Okay, that
So
was
the
pretty
difference in
Yeah.
acidic conditions, basic conditions, is that in basic conditions, attack less subside. Because we attack the less sterically hindered side in basic conditions. In acidic conditions, we attack the more subside. Right? So know the
Right.
differences. And know when you have acidic conditions versus when you have basic conditions.
Okay.
Mhm.
Got it. Thank
Yeah.
you so much.
Of course, guys.
You.
Good luck
Yes.
studying on your
Oh my gosh,
Good
Rika, I'm gonna
luck.
need it. I'm gonna need that good luck.
What are the classes?
The midterm tomorrow, the first is biochemistry, and
Oh.
I hate biochemistry. I don't like biochemistry at all.
But you
It's
like
so-
OChem?
Yes, OChem is so much better than biochem. Because I don't like the pathways like glycolysis, Krebs cycle, TCA cycle, oxidative phosphorylation. I hate it. I hate it so much.
Gosh.
Then after that, I have cardiovascular physiopathology. So it's like what the heart, pathologies, arteries,
that sounds
veins.
cool.
Yeah, that's way better than the biochem for sure.
Yeah, I
Yeah.
bet.
Jeez. That's a lot though. Well, best of luck. I don't want
Mhm.
to take up any more of your time. So
Yeah, thank
hope it all
you.
goes well tomorrow.
Yes. I'll let you guys know tomorrow if you guys show up tomorrow.
Yes.
Yeah.
How it went. Yeah.
All right. Well,
Thank
have a good
you.
night. Thank you so
Yeah.
much.
Of course. Good
Good
night, guys.
night.
Bye.
Bye.
Mhm.